Hello, welcome to this lesson on differentiation. This is ITE 1812, Mathematics for IT. We will first look at the learning outcomes. At the end of this lesson, you should be able to compute the limits of a continuous function, define and use the differential coefficient, and eventually apply power rule, quotient rule, inverse function rule, and chain rule in order to find the derivative of elementary algebraic functions. So at the very first stage, we introduce the concept of limit. So this is an important concept in calculus. So the limit of a function gives the sense that we approach something, but we never really get there fully. So we will use the word approach. So let's take a function fx. So this is defined as y equals fx. The function is pi. It's a function of x. Let's assume that there's a value of x which is x1, any arbitrary value. It is in the domain of the function. So we try to understand what it's meant by the limit of fx as x approaches x1, this arbitrary value. So we call it, the limit is L. So what do we mean by this? So values of fx gets closer and closer to L as x gets closer and closer to x1, both from below and above. So we can define two sides, the lower side as well as the upper side. Or we can say from the left side or from the right side. So both sides should be defined. The objective of the limit is not to define the value of the function at that point. For example, where x equals x1. Rather, when x approaches to x1, what is the behavior of the function? It is possible that the function may not even be defined at x1. But rather, we are interested in studying the behavior of the function in the vicinity of x1. So we will formally define the limit of a function. Symbolically, it is written as what you see on the slide. Limit of fx when x approaches x1 is equal to L. Let's take an example. We define a function y or fx, which is defined as x squared minus 1 over x minus 1. So if you are asked to investigate the limit of this function as x approaches 1, let's see how we do that in a very simple way. When you look at this function, you even notice that this function is not defined at x equals 1 because it will be division by 0 if we substitute 1 in this function. But that's not our concern. As stated above, we would like to see the pattern of the values of the function when x is in the vicinity of 1. So let's do that by using a table. So the function is x squared minus 1 over x minus 1. So we apply values closer to 1. So we start from 0.5 and the fx gives us 1.5. When we substitute 0.9, fx gives us 1.9 and so on. When we go closer and closer to 1, when the value of x goes closer and closer to 1, we see that the value of the function fx goes closer and closer to 2. So for example, when we substitute 0.9999 for x, we get for fx 1.9999. So we see that it goes closer and closer to 2. So this means that the limit of this function fx when x approaches 1 is 2. So this is the concept of the limit. So now we try to define the limit in a formal way. As x approaches x1, the limit of fx, which is L, is written as what you can see on the slides, the formal equation for limit. So this is defined if all values of fx are close to L. For values of x that are sufficiently close but not equal, should not be equal but close to x1. So the limit L should be a unique real number. We will see some examples for this later on. So here, if you want to be specific about the side, so we already introduced two sides, either from the left or the right, or from the upper side or the lower side. We can specifically talk about these different sides. So for example, from the lower side or the left side, we can write limit of the function fx coming from the lower side of x1 to indicate the limit from the left. So this is applicable when x is less than x1. And we can similarly write for the upper side or the right side where x is greater than 1. So these are called left hand and right hand limits respectively. So it is important that in order for the limit to exist, both left hand and right hand limits must exist and be the same. They should be equal. So from this, we can build up a theorem. This is the limit theorem of the limit. As x approaches x1, the limit of fx is L if the limit from the left exists and the limit from the right also exists and both limits are equal to L. So you can symbolically write them as given on this slide. So you also define the left hand side and the right hand side. They should both be equal to the same value, which is given as L in this case. So this is how we formally define a limit of a function. So these are some examples now. Example A is limit of 2 plus x when x approaches 3, which will be equal to 5. Similarly, limit of 3x, 3 times x, when x reaches negative 2, will be equal to negative 6. So simply by substituting the value of the limit, you can get the limit for these functions. They are pretty straightforward. Similarly, in part C, you have limit of x cubed minus 8 divided by x minus 2 when x approaches 2. When you substitute the values, you will get 12 as the limit for the function given in part C. So we can come up with some rules of the limit, which are pretty straightforward. So for example, if fx is a constant function, so we start by a constant function, that is fx is equal to c. And in this case, fx is not dependent on x. In other words, it's a constant. In this case, it is obvious, intuitive, so that limit of fx when x reaches to any value, limit of fx would be c, because it's not dependent on x, because it's a constant. But for the other instances, we can identify some of the rules that are applicable for the limit, assuming that constant c and two functions fx and gx, then the following rules of limits should also be stated, and they are simple and straightforward. So where number 2, what you see is a constant time the function fx, and you can write it as constant time the limit of fx when x approaches x1. And on number 3, what you have is the limit of summation of two functions fx and gx, but then you can separate those two functions and take the limits separately and simply add them. Similarly, for subtraction, multiplication, and division. In division, what you see is in point number 6, so a special condition that the divisor, the gx function in this case should not be equal to 0, otherwise it will not be defined. Otherwise this equation would be meaningless. So in number 7, you see the power. How does the limit behave for power functions? So for example, fx to the power n, and you can take the limit of fx and take it to the power n. So these are some simple rules on the behavior of limits when you have two functions and a constant. So these may be applied for multiple functions and combination of functions as well. Here are some examples. So in part A, you have limit of 3x plus x squared when x approaches 2. Then you can separately take limit of 3x and limit of x squared. So we consider both of these limits when x reaches 2, and what you do is simply add them up, which is 6 plus 4, and gives you 10. In part B, you have a square root of x squared plus 5. Take the limit of that function when x approaches 2. So here you have a power example. So this is 0.5, x squared plus 5 square root. That means it should be taken as 0.5 to the power 0.5. So what we can do is we can simply take the limit of that function and take the square root of that limit. That's what has been done in step 2 of part B example. And it will give you 3 as the answer. So in part C, what you see is another example function, which is 3x minus 4 divided by x minus 5. So what you can do is you can separately take the numerator and denominator and take limits of them and eventually substitute accordingly. And the answer will be negative 2/3. So these are application examples of the rules regarding limits. Okay, so now we define this concept of continuity of a function. So, but let's understand what do we mean by a continuous function. It is a function is identified as a continuous function if when we put that on a graph, it's a single unbroken curve. That is this very simple understanding that we can have. So in the next slide, we will see some graphical examples. When you see that, you will notice that there will be no jumps, what we call jumps or holes in the graphs. In other words, there are no discontinuities. So if the function is continuous, we say that the function is continuous over or on some interval of the real number line. If its graph can be traced without lifting the pencil from the paper. So you can basically draw the graph without lifting the pencil for a continuous function. Or in other words, you can't do that for non-continuous functions. If there's any point in an interval where a jump or a hole occurs, then we say that the function is not continuous over that interval. So we will see some examples later on. We can identify these kind of not continuous functions. We also call them simply discontinuous functions. So here are some examples. On the top, what you see is an example for a continuous function, figure 17.1. So you see that it's unbroken curve. There are no discontinuities. On the other hand, the graphs you see in figure 17.2, they are examples for discontinuous functions. So parts A, B, and C, you can see you can understand that there are discontinuities. You can't draw them without lifting the pencil. So in part A, for example, we can identify what we call as a hole. In when x is equal to a, that spot is not defined on that line, but it is defined somewhere else. So there's a missing part in this function. So we understand that as a hole. And in part B, you can also see the discontinuity. So after values greater than a for x, the function is different. All right. So there's a discontinuity, and you can't draw that graph without lifting the pencil. Also in part C, you see that the function is not defined when x is equal to a. So that's an also example for a discontinuous function. So now we move on to the formal definition of a continuous function. So a continuous function f is continuous at x equals x1 if the limit of fx when x approaches x1 exists, and the limit of fx x when x approaches x1 is fx1. So the function f is said to be continuous on its domain if it is continuous at each point in its domain. So for all the points, the function has to be continuous throughout that interval. If f is not continuous in a particular x1 in its domain, which is possible, as we have seen in the previous examples, we say that function f is discontinuous at x1, or that f has a discontinuity at x1. So these points can be visible, for example, here in the graphs, what you see on the bottom. For example, A and B. You can see discontinuities also in part C. So a discontinuity can occur at x equals x1 if either a limit of fx when x approaches x1 does not exist, or a limit of fx when x approaches x1 exists but is not equal to fx1. So there's a limit. There are two possibilities. Either the limit does not exist, or a limit exists but it is not equal to fx1. So in this case, we can identify that there is an discontinuity when x is equal to x1. So here are some examples for this concept. Part A is determine whether the function given by fx is equal to x squared plus 2 is continuous at x equals 2. So let's look at the solution for this example. So we take the limit in this case of function x squared plus 2 when x approaches 2, and we identify that the limit is equal to 6, and it is also equal to f2. In other words, when you substitute 2 for x in the function, you get 6 as the value. So therefore, we identify that the limit exists and it is equal to fx1 or f2. Therefore, the function is continuous at x is equal to 2. Part B of this example, we need to identify whether function gx, which is defined as 200 over x, is continuous at x equals 0. So we examine this. The function is 200 over x, but the problem is when at x equals 0, the limit cannot be defined because it's division by 0. Therefore, the limit of 200 over x when x approaches 0 does not exist. For this case, we identify that the function is discontinuous at x equals 0. Right. From the information, from the understanding of limits, we now move on to the concept of differentiation, which is also a very important concept. So let's try to identify what is meant by differentiation. We call this the derivative. The coefficient is called the derivative. So the derivative is identified as the instantaneous rate of change of a function with respect to one of its variables. So we'll soon come into a mathematical definition of this. The process of finding the derivative is called differentiation. So the method is differentiation. So by doing differentiation, our target is to find what we call the derivative. We will soon see how we do that. So we can estimate a derivative by computing average rates of change over smaller and smaller intervals. So we are going in for very, very small intervals. So let's start this by having a mathematical equation. So let h represent the size of the interval. Then we have average rate of change between x and x plus h. So x is very, very small in this case. So we can define the difference between x and x plus h when applied to the function. So we write that as fx plus h minus fx divided by x plus h minus h. So you see that the denominator will become simply h because the difference between x plus h and x is h. So from this equation, what we identify is the rate of change of the function with respect to x, because x is changing. So we identify here, or we define here that x is changed by the value h, and we examine, we try to investigate what happens to fx when x is slightly changed. So to find the derivative or instantaneous rate of change at point x, we use a smaller and smaller intervals. So to find the derivative exactly, we take the limit as h. The size of the interval shrinks to 0. So we say the derivative is the limit of this function as h approaches to 0. So what is the function? The function should be defined as the rate of change, that is fx plus h minus fx divided by h. So finally, instead of writing the phrase limit as h approaches 0, we use the standard symbolic notification for the limit. So this leads to the symbolic definition, which will be presented in the next slide for the derivative. So here is the definition of the derivative. For any given function f, we define the derivative of that function as f prime by, which is f prime x, when is defined as the limit of fx plus h minus fx divided by h when h approaches 0. So the change of x is very, very small, because that is the reason why we investigate what happens to this rate when h reaches 0. So it should be defined provided that the limit exists. So the function f is said to be differentiable at any point x at which the derivative function is defined. So we can also identify a special remark. If y is equal to fx, then the derivative of y with respect to x can be written in the following ways. So these are some of the common ways we denote the derivative. It can be f prime over f dash x, dy over dx, or simply y dash, because the function is y, or dfx over dx. Now, we identify some important rules of differentiation. Rule 1 identifies to deal with a constant. So derivative of a constant. So even if the function is defined for x, defined by means of x, if the function is a constant, which means it is not dependent on x. So if the function is c, fx equals c, where c is a constant, then the derivative of that function, which is c, is equal to 0. So derivative of any function with regard to any variable will be 0. So now, for example, d6 over dx. So the function here is a constant, which is 6. So the derivative of that value, that function will be 0 because it's a constant. So that is rule number 1 regarding a constant. Rule number 2 is regarding the derivative of an identity function, right? So we define this function as x. Fx is equal to x. So in this case, it is the identity function. Then the derivative would become 1. d over dx, x is equal to 1. Similarly, we can define for other variables, d over dy, y will be 1, and so on. Okay, so this is the definition of the derivative of identity function. So moving on to rule number 3, so we understand the power rule for differentiation. So for example, if x is equal to x to the power n, where n is a real number, then d over dx xn will be equal to n times x to the power n minus 1. So this is the power rule of differentiation. So we immediately look at an example. D over dx x to the power 5 will be 5 times x to the power 5 minus 1, which is 5 times x to the power 4. So that's how you understand and apply the power rule of differentiation. And then rule number 4 is the constant multiple rule for differentiation. So for example, when we have d over dx, c times fx. So c is a constant and fx is a function of x. Then we can take out the constant. That means we can write it as c times d over dx fx, where c is a constant. So look at the corresponding example. D over dx 2 times x to the power 3, you can write it as 2 times d over dx x to the power 3. And then you can differentiate x to the power 3, which gives you 3 times x to the power 3 minus 1. Eventually, you will get the derivative as 6 times x squared. So that's how you use the constant multiple rule for differentiation. Rule number 5, we identify that as the sum rule for differentiation. So when you have summation of 2 or more functions. So here we have functions f and g, fx and gx. So when you have d over dx, f plus gx, you can simply separate out and take the derivatives, take the separate derivatives of those functions fx and dx, gx, and then simply add them up. So where f and g are functions of x. So we take an example. Let y be x squared plus x3. Then fx is x squared. So let y be x squared plus x cubed, and then fx is x squared and gx is x cubed. Then if we want to take d over dx x squared plus x3, then what we can do is we can take the derivatives separately. D over dx x squared plus d over dx x cubed. So you simply take the derivatives separately. D over dx x squared will be equal to 2 times x2 minus 1, and d over dx x cubed would be equal to 3 times x3 minus 1. So eventually you can simplify that to be 2 times x plus 3x squared. So that's how we apply the sum rule of differentiation. Now we move on to a little bit more the next rule of differentiation, which is difference rule. It is quite similar to the summation rule. When you have the difference of two functions f and g, you can simply take the separate derivatives and take the difference of those derivatives. So where these functions are g and f and g are functions of x. So for example, we take y to be x squared minus x cubed. Then we can take fx as x squared and gx as x cubed. Therefore, if you want to take d over dx x squared minus x cubed, you can simply take the derivative of x squared and derivative of x cubed and take the difference. So derivative similarly as the last example, it will become 2x minus 3x squared. And then we move on to a little bit more complicated rule, which is about the product rule. So here also we have two functions of x, which are f and g, fx and gx. And when we want to take the derivative of the product of two functions, f and g, so there's a special rule that we use in this case. So when we have d over dx f times gx, that means fx times gx, we can write this derivative as fx times d over dx gx plus gx times d over dx fx. So here you see the relationship for the product. So you cannot simply take the product of the derivatives. In this case, you have to use this rule when you have a product of two functions. So let's take an example. So in this case, y is defined as 3x squared plus 1 times x cubed plus 2x. So you can identify fx as 3x squared plus 1 and gx as x cubed plus 2x. Then we want to take dy over dx. So that means d over dx 3 squared plus 1 times x cubed plus 2x. Then what you do is you simply apply the above product rule. Then you are left with 3x squared 1 times the derivative of x cubed plus 2x plus x cubed plus 2x times the derivative of 3x squared plus 1. So what you do is, it's not complicated. You simply substitute the values in the equation given in the product rule. So then you can have 3x squared plus 1 times the derivative of the function x cubed plus 2x would be 3x squared plus 2, and x cubed plus 2x times the derivative of the function 3x squared plus 1, which becomes 6x. And then you can simplify all the statements, you will eventually get 15 times x to the power 4 plus 21 times x to the power 2 plus 2 as the eventual derivative of the function y. That is the product rule of differentiation. And then we have the quotient rule of differentiation. So when you have functions fx and gx, and you want to get the division, the derivative of the division of functions f over g, for example, then you have to use this specific quotient rule to solve that kind of a problem. So here f and g are functions of x. So when you have fx over gx, and you need to take the difference derivative, you need to find the derivative of that kind of a function, you have to use this quotient rule, which is on the numerator, you have gx times d by dx fx minus fx times d over dx gx. And on the denominator, you have gx squared. Okay, so let's look at the example to get a better understanding. So we have y defined as 3x squared plus 1 over x. So in this case, you can identify fx as the numerator, which is 3x squared plus 1. And here gx would be x. So when you want to get dy over dx, that is 3x squared plus 1 divided by x, then you have to use the quotient rule of differentiation. So what do you have in the denominator? You have gx squared, which means our gx is x in this case. Then we have to put x squared. And what should be on the numerator? We have to have gx times, that is gx is x, remember, x times d over dx fx. Fx is 3x squared plus 1 minus fx times d over dx gx. So fx is 3 squared plus 1 and gx is x. So then you have to do the differentiation accordingly. So it becomes x times 6x minus 3x squared plus 1 over x squared. Eventually, when you do the simplification, you will get 3x squared minus 1 over x squared. So this is how you apply the quotient rule. Whenever you are given with a quotient division of two functions, then you have to apply the quotient rule of differentiation. And then also there's this important rule which we identify as chain rule. So in this case, let's try to understand what is meant by the chain rule. So assume z is a function of y. So we can write z is equal to fy. And y is a function of x. So we have three variables here, x, y, and z. So z is a function, z is a function of y, and y is a function of x. So y is equal to gx, z is equal to fy. Then if you want to get the derivative of z with respect to dx, that is dz over dx is equal to, we can write it as dz over dy times dy over dx. So this is the chain rule. So when you need to combine different variables. Okay, so let's understand this by an example. Let z be y to the power 4 plus 3 times y to the power 3, and y is equal to x squared. So here z is a function, or z is a function of y, and y is a function of x. Y is equal to x squared. Then if we want to get dz over dx, then what do we have to get? We have to get dz over dy and dy over dx separately and multiply them. So here that's what we do. We first get dz over dy, which is d over dy, y to the power 4 plus 3 times y to the power 3 times we need to have dy over dx, which is d over dx x squared. Then we can accordingly take the separate derivatives. D over dy, y to the power 4 plus 3 times y to the power 3 becomes 4 times y to the power 3 plus 9 times y to the power 2. And then d over dx x squared becomes 2x, 2 times x. And then what you can do is you can simply, because you know the relationship between y and x, because y is equal to x squared, you can substitute that relation or that value as x squared. Then you will get 4 times x to the power 6 plus 9 times x to the power 4 times 2x. And if you further simplify, or further in the next step, you will get 8 times x to the power 7 and 18 times x to the power 5. So this is how we apply the chain rule with regards to differentiation. So in this case, you have a combination of functions. For example, function z, z is a function of y, and y is a function of x. And eventually, if you want to get dz over dx, you can write it as dz over dy times dy over dx. So this is a chain rule. So when you apply differentiation, when you need to find differentiation of functions, all these rules regarding differentiation will be useful and applicable. And then we define the differentiation of an inverse function. So this is rule number 10 about inverse function. So let's define a function fx as a one-to-one function. Then dy over dx is equal to the inverse, 1 over dx over dy. However, dx over dy should not be equal to 0. Otherwise, the function will become meaningless. So let's take an example. For example, take y equals 2 times x. It is clear for us that dy over dx is 2, right? Because you can simply differentiate that. It is left with the value 2. Now consider the inverse function. So what would be the inverse function here? Because y was equal to 2 times x, x will be y over 2. So that is called the inverse function. Then we know that we can take dx over dy. When we take dx over dy, what happens? Y goes away and we are left with 1 over 2. Therefore, it is clear that we can identify that dy over dx is equal to 2, which is equal to 1 over dx over dy. Okay, dx by dy is half, or 1 over 2, and it becomes, when you take the inverse of that, that means 1 over dx by dy will become 2. So this is the inverse function rule when it comes to differentiation. That brings us to the end of this lesson. In this lesson, we get introduced to limits of a function and then moved on to identify the concept of differentiation. And we went through all important rules of differentiation. In the next lesson, we will be covering derivatives of logarithms, exponential, and trigonometric functions. Thank you.